Hello all. So students, faculty, staff, alumni, and others who participate in any of the following seminars with their camera on or use a profile image are agreeing to have their video or image recorded solely for the purpose of creating a record for participants in the seminar to refer to, including those enrolled students who are unable to attend. If you are unwilling to consent to have your profile or video image recorded, be sure to keep your camera off and do not use a profile image. Likewise, participants who unmute during the seminar or class and participate orally are agreeing to have their voice recorded. If you are not willing to consent to have your voice recorded, you will need to keep your mute button activated and communicate exclusively using the chat feature, which allows participants to type questions and comments live. So without further ado, Professor Hansen, please go ahead.
Okay, so good afternoon, everyone. I'm very happy that all of you are joining us this afternoon. Just one procedural note, James Heckman is going to present on December 1st, and we will start the seminar at 11 and until 12:45, and then from 12:55 to 2:40, Richmond, our student, will present. Richmond Forger, and he will present from 12:55 until 2:40. So I'm very glad that today we have Lars Hansen with us. Lars is a David Rockefeller Distinguished Service Professor at the University of Chicago at the Department of Economics and Statistics, and he's also associated with the Booth School of Business. And Lars, if I'm wrong, please correct me. He's the recipient of what I call the Nobel Prize in Economics, together with the late Eugene Fama from the University of Chicago and Bob Shiller from Yale University for the empirical analysis of asset prices. As we all recall, Bob Shiller presented his paper in our seminar about 1 month ago on October 13, 2020. Lars Hansen is an expert in economic dynamics, utilizing approaches for macroeconomic, finance, and statistics. He improves and constructs models that measure risk and uncertainty. These models have important implications for financial markets, fiscal policy, and the macroeconomy. Lars has collaborated for many years since their days at the University of Minnesota with Tom Sargent, who, as some of you know, was the chairman of my PhD thesis, together with the Nobel laureate Chris Sims. By the way, Lars is a student of Chris Sims, and Ed Prescott, who also got a Nobel Prize, and I am still waiting for Neil Wallace to get one. Hansen and Sargent and their co-authors have developed methods for modeling economic decision-making in environments in which uncertainty is hard to quantify, as we will see today. They explore the consequences for models with financial markets and characterize environments in which the beliefs of economic actors are fragile. Some bibliographical notes. Hansen joined the faculty of University of Chicago Department of Economics in 1981. He served as a department chairman at the University of Chicago Department of Economics and the director of the graduate studies. In 1984, Lars Hansen and Ken Singleton were awarded the Frisch Medal for the Econometric Society from the Econometric Society for their paper Generalized Instrumental Variables Estimation of Nonlinear Rational Expectations Model. Hansen is a fellow of the National Academy of Science and the American Finance Association. He is a member of the American Academy of Arts and Sciences, and he is past president of the Econometric Society. He holds a bachelor degree in mathematics and political science at Utah State University, and as I mentioned before, a doctorate from the University of Minnesota. We provided the audience with his recent paper, Pricing Uncertainty Induced by Climate Change, which was published last February 2020 in the Review of Financial Studies as a background to his new paper that is still under construction that he is going to present today. Today, Lars is going to present the co-authored paper with Michael Barnett from Arizona State University and William Brook from the University of Wisconsin and University of Missouri. The title of his talk is How Should Climate Change Uncertainty Impact Social Valuation and Policy? So Lars, I'm very glad that you are here and I appreciate it very much.
Thank you. Thank you for the kind introduction. Let me see if I can get my slides up here. So, as was mentioned, what we're interested in here is studying climate change, but uncertainty. And how should uncertainty, our incomplete knowledge of how climate change affects the economy spill over to the design of economic policy. I have two important collaborators that were mentioned, Mike Barnett, a former student of mine, and Buzz Brock, a longtime expert in economic dynamics. So let me kind of get down to business here. What is the challenge? So the human impact on the environment is not internalized by markets. What that means is that there's a discrepancy between the social cost and the private cost. How big is that discrepancy? Now, there's two sources of uncertainty I'm going to be talking about today. One is CO2 emissions today affect the climate in the future. Also, climate change in the future is going to alter economic opportunities and social well-being. These two different forces are in effect multiplicative, and they can reinforce each other. And so I believe it's important to think of them or to study them simultaneously rather than separately. So what are we aiming for in this research? So a computationally tractable laboratory to explore subjective uncertainty. And these subjective uncertainties can take different forms: potential model misspecification, ambiguity across models, and the like. Then the goal becomes to assess the impact of uncertainty on climate policy outcomes, but to also isolate the forms of uncertainty that are most consequential for these outcomes. This then opens the door to explore policy relevant consequences of models in an open and honest way.
Lars,
so kind of in a nutshell,
Lars, I have a question to you. What do you mean by honest way? It sounds subjective.
Sounds suggestive. So give me a minute and we'll come back to that.
Okay.
And I'm going to appeal to Hayek in just a moment.
Okay.
So we're going to engage in quantitative storytelling with multiple stories. So think about each model. Each model tells a story. It tells us a story that enhances our understanding. It tells a story that what are prudent policies. Different models have different implications. How do we balance all of these? When indeed each model is itself an abstraction or a simplification. So that's the challenge we're facing here. And this challenge, I'm going to talk about in the context of climate change, but it carries over other policies as well. COVID would be would be another example. That's playing out at a much faster time scale, of course, than climate change. But these same concerns carry over to monetary policy and other policy challenges as well. So when we confront policy uncertainty, there's this tension. There's a limited understanding of mechanisms by which policy influences economic outcomes, but at the same time, there's demand by the public and government for precision, for precise answers. This is what we're fighting against. Now, in order to influence policy, economists, other scientists will often put the uncertainty to the wayside and project themselves with great confidence in their views. This is where the honesty comes into play. That type of projection doesn't really acknowledge the limits to our understanding of phenomenon. So how can we enhance our tools in order to think about that, how to incorporate those knowledge limits? So here, let me appeal to Hayek. I'm haunted by Hayek's forewarning here. So Hayek, when you win the Nobel Prize, you have to write something. You're supposed to write this essay. The charge of that essay is, why did you win the Nobel Prize? Which no one really wants to write about that per se. They might say comment a little bit on that, but then they write an essay on a variety of their topic of choice. Hayek's essay is very interesting. He just wins the Nobel Prize in economic sciences, and his essay really challenges the sense of which economics is a science. And it's a fascinating reading. There's portions of it I would definitely disagree with. Hayek was very negative on quantitative methods and econometrics and the like, which I'm quite much more sympathetic towards. But there's this quote here from Hayek that I think is really revealing and of something that I've thought about a lot. Even if true scientists should recognize the limits of studying human behavior, as long as there's a public out there that has expectations, there'll be people who pretend or believe that they can do more to meet popular demand than what is really in their power. And this pretense of knowledge, it could be good, but also could be harmful. So for quantitative policy analysis, how do we acknowledge the limits to our understanding? That's the aim here. Okay, where does uncertainty emerge? So I like to think about this as quantitative storytelling of multiple stories. So these are words I just used a couple of slides ago. Now, how does the uncertainty show up? Well, the usual one we learn about in microeconomics classes has to do with risk and risk aversion, and in finance classes, risk premium and the like. So I'm going to think of risk as formally as uncertainty within a model. Each model has these random impulses. With those random impulses, I can figure out probabilities. So a model fully specified tells me probabilities. I have uncertain outcomes, but known probabilities. The second component I'm going to call ambiguity. I think of this as uncertainty across models. There's multiple models, each give rise to multiple stories with different implications. Now, of course, statistics, the discipline, has been kind of about how to address this. And indeed, there's been a beautifully elegant Bayesian paradigm whose philosophical origins go back to DeFinetti and Savage and others. But even DeFinetti and Savage were very clear that their framework required the subjective probability inputs, and and they can only be known for a lot of problems very crudely. And Savage, in fact, went on to say that the apparatus itself is perhaps most valuable for very simple problems, for very simple characterizations of uncertainty, which is quite different than the world we face. So to my taste, or to my views, just filling in things subjectively doesn't really resolve the uncertainty. What should those subjective inputs be, and then how might they matter? And finally, each model is wrong. It's a simplification. In macroeconomics, we know this for sure. We write down these highly simplified models of a very complex macroeconomy. We view these models as insightful. We view them as revealing. But we also know that they're very big abstractions. So when we make these abstractions, are we making mistakes that are consequential or ones that are inconsequential? So in many respects, this might be the most important component to uncertainty and the hardest one to wrestle with formally, although there's some work that's been done along those lines. Today, I'm going to feature ambiguity, but I've explored this misspecification concerns in other work. Please interrupt me whenever you see fit with it. I'm more than happy to entertain questions along the way.
All right, so again, I encourage everyone to ask questions.
So these probability models that we use in practice are misspecified. This ambiguity as to which one is best. So how do we navigate this uncertainty? How can we address this in a more formal way? So the aim then is to use a model in a sensible way rather than just throw it out. We don't want to give up on the tools of probability and statistics. We still want to use those to limit the type and amount of uncertainty that is entertained. Finally, just like risk aversion is a type of theory of caution, There's also aversions which you have to confront about a dislike about this uncertainty about probabilities over future events. Implementation of this boils down to targeting the uncertainty components that have the most adverse consequences to the decision maker. So we can imagine some highly complex probabilistic structure. It could be, there's various different dimensions to the sensitivity analysis. How can we reduce that substantially into something much more manageable and tractable? We want to let the computations help us do that. And the way they do that is take the overall decision problem and really isolate the places where the subjective uncertainties are most consequential. So that becomes part of the formalism. Now, along with this kind of ambiguity aversion, there's this kind of uncertainty trade-off which you're facing with this aversion. So we use mathematical models that are informed by expert judgment, empirical evidence. We can use them to make best guesses.
Professor, I had a question.
Yes.
So you mentioned ambiguity,
Yes.
which is essentially having a range of models, and essentially having multiple stories being told across this range of models. And you also mentioned Bayesian modeling, and Bayesian probability. There is the notion of hierarchical modeling, where you have hyperparameters, which can learn how the next level of models relate to each other. Is there any association that you see between learning hyperparameters as it relates to ambiguity quantification?
Yeah, so I certainly think that forming hyper model, doing this hierarchical structure and looking at layers of priors and the like can all be very useful ways to represent models and uncertainty about them. Still, at some level, for a lot of important policy questions, there's going to be subjective inputs, priors of some form. The question is, if that's the place where you want to think about the sensitivity. So yes, given enough structure, we can start applying Bayes' rule and do a lot of really nice calculations. But the problem is, to do that, you have to buy into a lot of specific structure. It may be flexible along some dimensions. The more flexible it is, typically the more challenging it is to fully learn about it. So at some level, for decision problems, there's typically some places in which there's remaining uncertainty. And one can pretend it's not there, but I think it's most certainly there. Now, a lot of work done in Bayesian statistics and also applied economic data is about data summaries, and less about how you use those to frame policymaking. I do think they use those type of methods in a policymaking framework. One has to think about writing down decision problems, and often is almost compelled to put more structure on the problem. So it's important. So this is about going beyond just what are useful data summaries to really what are consequences for policy. So,
can you hear me?
Yes, Lilia, go ahead.
Yeah, so I wanted to ask about like concept in science when they talk about VVUQ, which is verification, validation, and uncertainty. They talk about uncertainty about the choice of the model and process of determining whether the computational algorithm delivers a right solution. So your concepts of misspecification, ambiguity, they are very similar. So basically, ambiguity is the same as validation there. Can you comment on that? Or?
Yeah, so absolutely. I'm happy to put issues about model choice, model selection, model weighting, all on the table as very interesting methods to apply. I absolutely do like quantitative Bayesian methods. I think they can be very revealing. But the notion of this is more like the notion of a robust Bayesian. That is a sense in which along the way, there's going to be some prior specifications that could matter for the decision problem. And in order for this to get off the ground, you have to have a decision problem, because when you talk about sensitivity to what? And so once you lay down the decision policy or policy challenge, then you put on then you can answer the question, sensitivity to what? And now there may be some sets of circumstances which in data are just so rich that they just reveal everything you need to know. The data swamp priors and subjective inputs, and this all becomes a secondary consideration. I would say that in the context of climate change, I mean, I'll start showing you some numbers later. This is not the case. I would say that as we've watched the evolution of COVID, that was not the case. And so in a lot of policy problems, we don't, even though there's data richness somewhere, it's not data richness everywhere. And so therefore we still have to rely heavily on models and subjective inputs and things that we don't have full confidence in. So I absolutely do want to lever quantitative Bayesian methods. I don't want to discard them in any way, but I don't see them as the full answer to the question that I really care about here.
Lars,
yes.
Lars, if I may, I'm Christos Giannikos. I'm the executive officer of the program. I wanted to thank you. We are deeply honored to have you with us today.
Mm-hmm.
I have a question that is related a little bit to the setting that you chose. You talked about ambiguity.
Yeah.
And I wanted to ask you, what is your view on, I mean, people have used other ways like fuzziness, vagueness, generality, ambiguity. So what is your take? Why did you choose ambiguity out of all of this?
I think there's a huge overlap between these different constructs. And to some extent, it's like, labeling in languages, although there are some operational distinctions as well.
Mm-hmm.
So what I found to be helpful is decision theory formulations, and I see some, at least the ones that I followed that have been most interesting are ones that have kind of gone to this ambiguity framework. I guess this in part goes back to Gilboa Schmeidler, work by Marinacci and a variety of others, Klebanoff and a variety of others. So I guess I've inherited their language, but there is an overlap between what goes on there and what goes on in some of these other literatures as well. And the problem with decision theory alone is decision theory is not directly operational. It's all about logical conceptual underpinnings. And so kind of taking that decision theory into practice requires some careful thinking and thought as well, which I've spent much time working on and writing on. And today's paper is a bit of an illustration of ways to do that. So I'm not sure I'm not going to say this is the way to do it, but this is a way at least we found to be attractive and appealing. And I do believe there's a huge overlap between this and the type of constructs that are showing up in these other literatures you're talking about.
Thank you.
Okay. So this uncertainty trade-off. We can use mathematical models informed by expert judgment and empirical evidence to make best guesses. Alternatively, we can use them to determine potentially bad outcomes. So, watching through COVID modeling, especially last spring, this distinction was not terribly clear sometimes. Sometimes people would make best guesses. Other times when people say, well, this model, look what bad could happen. Now, both of these type of calculations are interesting. And there's a trade-off between them. So I kind of like to think about trade-offs. How much weight you put on the best guesses versus how much weight you want to be concerned about potentially, bad outcomes. And that's where this ambiguity aversion comes into play. It's a way to confront that trade-off. And I can't tell you exactly the right magnitude to trade that off, but these methods want to expose that trade-off. And then for different policy problems, we can make different assessments on where we want to be here. But I think that distinction is important, these best guesses versus potentially bad outcomes, different ways to use a model, and the fact that for prudent decision making, one has to implicitly trade off those type of considerations. So there's the decision theory. I mentioned this briefly. I'm not going to go into the details of it. Here's some some discussions. The stuff that we're doing is most connected. The application today is most connected to this work of Klebanov, Marinacci, and Mukherjee. I've done some work with Meow that's talked about extending it to continuous time environments. There's axiomatic defenses for differential risk aversion. What I like, and this is an equivalence that we've shown in some of our other earlier work, is that the smooth ambiguity model has a robust Bayesian equivalence to it for certain specifications, that the smooth ambiguity can be generated or constructed from a recursive, robust choice of priors. And that's this, and that's the avenue which we'll be taking here. I find that a useful way to think about what's going on in these smooth ambiguity problems, to connect it back to robust Bayesian methods. And so what this allows us to do is to collapse this high dimensional uncertainty into something that's low dimensional, 1 or 2 parameter dimensional uncertainties by working this apparatus. Formally, mathematically, it boils down to solving a so-called two-player zero-sum game, differential game. It's the same thing that actually underlies Lagrange multiplier theory. There's a stochastic differential equation for state evolution. This could be discrete time too. That's not critical. One player is going to be concerned about social well-being, but there's going to be this other player which we invent for the purposes of doing sensitivity analyses that investigates the adverse consequences of the uncertainty about the probabilistic inputs. And so that player is going to be engaged in minimization, whereas the initial player will be engaged in maximization. So the one player is going to figure out what's a prudent policy, but then along the way, looking at where that policy could break down. And this just gives us a formal way to do it. As I indicate, I'm not going to get into the details here. We use this construct called Rudder of entropy, or Kullback-Leibler type methods to bound or limit probabilistic uncertainty. And at least for the calculations here, I'm going to be using numerical PD methods with some extra twists. Again, this is not something I'm going to get the details on for this particular talk. So that's kind of some mechanics. So just to indicate how this is going to work, when I solve this problem I just described, what comes out of it is a probability. It's going to be an adjusted probability. I'm going to take some baseline probabilities, maybe computed from Bayes' rule or the like, and I'm going to start doing some adjustments to them. Okay. And how much adjustment I do is going to be connected to how averse I am to this ambiguity. And now, so out of this is going to become both a prudent course of action as well as a probability that helps that effectively implements it for us. This probability adjustments then can be made over economically relevant outcomes in future time periods. Now, what this probability is going to do is it's going to make the uncertainty adjustments in valuation. And so it's going to be there's going to be very strong parallels between what we're doing here, what shows up in the theory of finance. Except here the probabilities that we're computing here actually are ones to represent economic values. And I'll be giving you some examples later in this talk.
Lars, how sensitive it is to the initial conditions, the initial assumption about?
Which assumption do you have in mind?
Say it again.
Which assumption do you have in mind?
The probability is that you are updating them, right? To make them.
Oh yeah, this is going to be sensitive. Yeah. So typically we start with some type of baseline probability, and then we start looking at changes away from it. So the straight Bayesian approach, the baseline would be it. And so now what we're doing is we're looking at what happens if we start changing things a little bit, and then see what consequence that has for the decision problem.
And do you do some robust analysis if you change these initial probabilities?
One can do that as well. I mean, so our starting point, it doesn't have to be actually a baseline probability. It could just be, the starting point could be a family of, just a family of such baseline probabilities. And then, But yeah, I mean, the sense which is no free lunch here. We got to start somewhere, and so, but yes, we don't necessarily need a single benchmark starting point. And other work have shown that you could basically start with a family of such entities.
I'm thinking like in chaos theory, like there will be a tipping point that maybe it will, the environment will pollute it to infinity, or maybe something will happen.
Oh yeah, so I'm going to give you some examples here that one of them is going to look a little bit like a tipping point. So basically, for the purposes of today, the best way to think about it is there's just a whole family of models, a whole family of such models that I don't know how to weight. I don't know what weights to attach them. And so, but the thing is, I have to start off with some baseline set of probabilities over those models, and then we start twisting those, changing those, and seeing how much difference that makes. Okay, I'm not going to get too lost in this, but we're going to have some underlying Markovian dynamics. It's written in continuous time. We have these local normal shocks. One could have jump components. One could do this in discrete time. Think about for the moment, there's some, this theta parameter is going to index alternative models. X is a state vector. W are these kind of locally normal shocks, the DWs. And the key thing for us is we're going to be using dynamic programming type methods. So there's going to be a so-called continuation value. There's going to be value functions that can be, and with those continuation value processes, taking the value functions and evaluating them at the relevant state variables. That local evolution, when we do our sensitivity analysis, is that local evolutions is going to be central because that's what the decision maker is going to care about. How are those continuation values going to evolve, and what happens if I want to change probabilities. So I've just written here something that comes from so-called Ito's lemma. I've just written how continuation values evolve here. We're starting with a value function that depends on value function B that depends on the Markov state. Okay, again, this is kind of a math-heavy slide. Let me just try to talk your way through it a little bit. So ignore the X right here. That's a typo on my part. I apologize for that. So we take this part of this evolution, this local evolution of continuation values. And one possibility is we just average over all the models. Just do simple model averaging. I've got some probability distribution, Q sub t. It might be updated via Bayes rule or the like. I could just average out over that. Or alternatively, I could make this conservative adjustment. Now, what shows up here is the type of adjustment that would come out of a so-called smooth ambiguity model. It looks very much like a risk aversion adjustment. I take an exponential adjustment. The C sub A parameter tells me how important that is. And then I'm going to convert it to a certainty equivalent. And that's what the log's doing out front, as well as a multiplication by C sub A. Now, what's nice is that problem, that smooth ambiguity adjustment, can come out by solving a minimization problem. I'm going to minimize. I'm going to take the original probabilities, the DQs. I'm going to reweight them by this G of theta, by a relative density. I'm going to look at what happens. I'm going to look at what happens as I start changing that around. What happens is going to depend on the course of action and the like. And so now, instead of just averaging over all the models, I'm going to make this. I'm going to do this. I'm going to add in this minimization step, and allow this function G to move, but I'm going to limit how. I'm going to penalize how much it moves, and that's what this. This is log. This kind of log G term is showing up there. This kind of log G term gives rise to the so-called relative entropy adjustment. So basically, smooth ambiguity models that show up in the Klebanov, Marinacci, and Mukherjee literature are equivalent to changing probabilities. And they engage in a type of exponential tilting here. You take a continuation value evolution, and then you tilt it. You use that to tilt the probability distribution over the different models as indexed by thetas. And you're going to tilt it towards ones that have the more adverse changes in the continuation value. And so that's kind of what goes underneath the hood in part in some of the computations that So QT is our baseline. We make this conservative adjustment. The magnitude of C sub A, of course, is going to have a lot to say about how big that adjustment is. Derive C sub A to infinity. That's going to correspond to just doing a simple average, as a more straightforward Bayesian procedure would entail. Okay. So now I want to get down to this policy question. So I'm going to think about climate change in terms of the social cost of carbon. And the social cost of carbon says is well, there's a market price for emissions, and then there's the ones that the price that takes into account damages to the environment. The latter is then called the social cost. The difference is then that there's a whole literature on Pigouvian taxation that's kind of premised on that, on the difference between those two. But I'm going to take the that wedge there between the social cost of carbon and the kind of private cost of carbon as a measure of how big the policy challenge is. Now, the social cost of carbon, one can think about that as an asset price. So here's how that works. Imagine you emit CO2 in the atmosphere today through a consumption of fuel, say. That's going to affect temperature in the future. Temperature in the future is going to affect economic opportunities going forward. This might be nonlinear. And then we can get, and so the emissions a day, a small change in emissions a day generate out the social cash flow coming through this so-called nonlinear impulse responses. We have to then incorporate marginal utility adjustments. Now, along the way, we have to entertain these forms of uncertainty coming from economic damages and climate change. And there's lots of literature in environmental economics about what's the discount rate. Well, here we're doing so-called stochastic discounting. There's uncertainty involved. And that uncertainty adjusted probability that I talked about before that came out of that so-called two-player game is what we use here to compute the discounted present value to get the social cost of carbon. So the social cost of carbon is going to glamorize these social cash flows using stochastic discounting, and it's going to adjust for the uncertainty through this change in probabilities. And so the computations we do kind of all kind of do this for us. Okay. So social cost of carbon can be thought of as an asset price. Uncertainty is accounted for by a change in probability. So I'm going to feed this into a fairly simplified or standard economic model with a couple twists, okay, in order to do some calculations. I'm going to work at the so-called AK model with adjustment cost. So capital today gives rise to output. Included in output are going to be three things. Consumption directly impacts economic well-being. I'm going to also use some of the output to engage in exploration to try to find new reserves, the fossil fuel reserves. And then I'm going to also spend some of it for investment in order to augment the capital stock. So part of the model then is going to be making decisions about how to allocate that output. Now the exploration goes into augmenting the stock of reserves. The more we explore, the more we discover these stock of reserves. And then we draw down the stock of reserves via these emissions, which then also affects economic well-being. So far, I'm not talking about climate change. This is an economic model. Piece together the way we do it, this model has a nice balanced growth path that behaves in a nice way that we're kind of familiar with from macroeconomic modeling. Next, we want to stick in climate change. So at the same time, these emissions are, I like to drive cars, and so therefore I like to consume fossil fuels. These emissions also damage the climate. And the climate in turn damages the productive opportunities of the economy. So in a nutshell, that's how the model is going to work. The blue pieces are pretty much standard simplified, just a simplified macroeconomic setting. The red part is what sticks in the climate change. We're gonna have just some notation. There's gonna be exogenous forcing process. I'm not gonna say much about it today. Now I'm writing some equations out that just capture what was that diagram. There's the evolution of capital. This kind of log term here is just captures the adjustment cost. IT is investment, KT is capital. Production is broken down to these three pieces: investment, in exploration, consumption, and then this augmentation, then the augmenting of the capital stock, C, I, and J. Now reserves. So now we put reserves on the table. The exploration in conjunction with the current stock reserves then leads to new discoveries, and that increases the stock of reserves. But then we draw down the stock of reserves through our emissions, so minus ET here. Now there's this very famous kind of hoteling model of exhaustible resource that would fit into this if I'll just close down the exploration. So basically we let psi 0 equal to 0. And then typical hoteling models don't have the stochastic component either. But anyway, hoteling's model is kind of a limiting case of this. Okay. Now we want to get to climate change. Now there's different ways that we could model climate change. One is, and that's the one I'll be focusing on today, is you take the production possibilities and you reduce them across the board through so-called damages. The other way is that you take the growth potential of the economy, you look at the growth of the capital stock, and then you have climate change hinder that. So we're going to focus more on the former, which is consistent with a lot of the work of Nordhaus and Dice models and the like. The second channel is very interesting and can be incredibly potent. It's a hard one to think about how to plausibly calibrate, which we talked about in our earlier published paper. But it's potentially interesting economically. Okay, I'm just going to adopt a simplified specification of preferences. There's we care about preferences will be log. We also have preferences for emissions. Then there's just going to be this end term that's going to capture damages. And so this proportional reduction productive capacity that's going to go all the way to consumption. So CT that divided by NT tells us the so-called amount of consumption, the so-called damage consumption, which after taking into account the environmental degradation. So we're going to take a relatively simplistic stab on this damages. And this follows a lot of the environmental literature. It has its limits because it's a very static notion. So we're going to take temperature, and temperature changes are going to affect the productive capacity. Now, adaptation is kind of embedded in here perhaps, but you think of adaptation as having a dynamic component to it. So it's that part's left out here. I actually think it's a big omission, but more about that later. Okay. So I'm going to model this damages in terms of this degradation in terms of logarithms, and it's going to be kind of so-called piecewise quadratic. There's going to be a threshold here, lambda bar. One can think of that as a type of tipping point, if you like, and it could be, that beyond some point, things get more severe. Okay. And so prior to that point, we're going to think of this lambda function as quadratic. After lambda bar, then we're going to stick in this, there's going to be this extra kick coming in from the damages that might occur beyond this threshold lambda bar. There's a lot of the climate science literature will make arguments about, well, the way to think about policy is through carbon budgeting. We had to only allow emissions in order up to 2 degrees, in order to allow, say, 2 degrees changes in temperature, Celsius. And then we can just kind of shift emissions accordingly. Now, if we actually knew all the relevant parameters of the model, the carbon budgeting approach would pretty much lead us very close to a so-called hoteling model induced now by the carbon budget. It's a little bit more with uncertainty. It's that mapping isn't quite so clear. But economists like to think in terms of smoother trade-offs, and we'll be doing the same here. So let me just give you a figure here. The carbon budget, as I talked about, is at 2 degrees, you fall off a cliff. Now, we're going to have 2 other damage specifications. They're going to be exactly on top of each other. That lambda 2 plus can be different. They'll be exactly on top of each other until 2 degrees, and then they're going to separate. There's a low damage trajectory. This is one which is motivated by some of Nordhaus's calibrations from expert surveys. Expert surveys are tricky here because I could find climate scientists that would tell you that those low damages are totally crazy. So it kind of matters who you designate experts, of course. The blue line here is more motivated in part by some of Weitzman's arguments that the Nordhaus damage functions are really not steep enough, and they ought to be substantially steeper. In part based on uncertainty considerations, although the Weitzman work doesn't really fully work those out in a climate setting. But anyway, it's the thing of the blue line is motivated in part by some of the Weitzman type arguments. Now we're talking about changes that we haven't witnessed yet. These going beyond 2 degrees. So we can speculate whether we're on low damages or high damages, but there's not some readily available evidence. We can just say, well, this tells us what, which trajectory we're on. So we're going to approach this instead of knowing it's low damage, knowing it's high damage, is we're just what 50-50 on each one. Okay? And that's going to be our type of damage uncertainty. There's other ways you could do it. You could take that lambda 2 plus parameter and put some baseline distribution over it or the like. But this is the type of uncertainty we're not going to learn about until we start really doing serious damage, much more serious damages to the economy, in which case it may be very costly to act. So climate models are highly complex. There's like no way we could go and take a climate model and put it inside this economic model. Some of the climate models take a huge amount of time to solve. They're nonlinear. They're either chaotic or near chaotic. So that's just not a viable way to go. So we have to adopt some simplifications here. So we're going to use some results, we're going to draw on some characterizations from the climate science literature, adapted or modified to our setting. So there's going to be 2 sources that show up in the climate dynamics. One is the mapping from emissions induces changes in carbon concentration. So what happens there is you emit into the atmosphere, and then some of it eventually gets pulled, gets reduced through carbon sinks, through vegetation absorbing the CO2 and the like. And that plays out over, that can play out over a fairly long time scale. Now it's also the case that if we change the carbon concentration, that's going to alter temperature in the future. Now we need to put these 2 things together and forming a so-called convolution of these 2 different effects, these 2 different ingredients. Then what we're going to draw on are these so-called pulse experiments for alternative climate models. So to do model comparisons in the climate literature, what has often been done is to basically run the counterpart to what economists think as impulse response functions. I feed the models some impulse at some initial date of the of carbon emissions above baseline, and trace out the responses, and then I compare the responses across the models. And those are the type of comparisons I'm going to be showing you. Right from these pulse experiments, I guess there are 100 gigatons pulse experiments fed to these models. So we're going to do model comparisons through the outcomes of pulse experiments. So what I've done here is we're going to take 153 different models. Each of these models, and we're just taking this from the climate literature. It's not something we did. We're just taking the numbers from there. We're taking 153 different models, And then we're going to run these and then tabulate these responses. Here's over 100 time periods. These things level out quite a bit. So a typical response here you'll see is the peak effect occurs after about 10 years. Then it might come down a little bit, and then after that it's remarkably flat. The flat part of this has been noted in other model comparisons as well. It's often attached to the name of Matthews and the Matthews approximation, that roughly speaking, that the temperature changes are roughly proportional to the cumulative emissions of CO2. Here showing up in these pulse experiments is going flat. Now they go flat, but they're very heterogeneous. So I'm reporting here are percentiles. So think about, I could show you 153 different curves, but that would of course be quite ugly. Think about the green line here, okay? The green line is the so-called 10th percentile. 10% of the responses were below the green line, 90% above. Take the purple line, the purple dotted one, 33% below, 67 above. Take the blue one, 67 below now, and 33 above. Then finally the red line, it's going to be 90 below, and then just 10% above. So this shows you that for the responses, the long-term responses, where long-term is only about 20 years, 15 to 20 years, are quite substantial. There's quite substantial uncertainty about these. And the historical, and learning about these through historical evidence to date has been very, very slow. There's some very interesting Bayesian papers on climate sensitivity analyses. One that was, it was very, very nicely done. But when it came to a climate sensitivity parameter, it showed that if I put it on a so-called diffuse prior, I got unreasonable posteriors. And to get a reasonable posterior, I need a very informative prior. And then, of course, the posterior tracked the prior. I mean, not literally, but fairly closely. So this is stuff where evidence just doesn't play out very quickly. Now, as you start damaging the environment more and more, then maybe we would learn much more about this. But as I say, it may be costly to act at that point in time.
Lars,
so now what I'm going to do is
Lars, could you explain to me better this figure, because I don't understand it really. What does it mean? Let's look at year 40. What is the number 1.5? Approximately 1.5 for the green line.
Telling you, I'm not telling you the units here, but that's telling you. So it's I'm not telling you the units of the pulses. What the 1.5 is telling you the temperature change associated with that pulse. I think these are 100 gigaton pulses. And the key thing here is, there's some sensitivity for these across pulse sizes. They can matter, which I'm not going to be showing you. This is one of the more smaller pulse sizes. They often hit the models with even much bigger pulses.
So you show
this is just the numerical counterpart to an impulse response function that we use in macroeconomics all the time. So I take some big climate model. It's got some baseline paths for things, and then they'll stick this pulse on top of it. The pulse is not literally an instant; it's spread out over a year or so, I think. But it's.
I see. Okay.
And then we just produce them for we compute them we tabulate them for 153 different models.
And may I ask you, so these models are completely different, or
the models are what?
The models are completely different. I mean, or they differ just in the values of parameters.
So I'm going to miss the right number. So we have to put together models that tell us the dynamics going from emissions to CO2 in the atmosphere, and models that are telling us CO2 to the atmosphere in a temperature, because we have to put the two things together to get these plots. And so we look at all combinations of a discrete set of models. And by the time we multiply up all those combinations, you end up 153 different trajectories.
But what does it mean? It means that, I don't know, between 40, what does it mean? Like, what does this 1.5 degree Celsius mean?
I'm going to tell you what it means in terms of the social cost of carbon. I'm going to tell you how it impacts the emissions and the like.
Okay.
And, the magnitude of the degree Celsius depends on the size of the emissions, and the size of the pulses, of course. So what I'm trying to characterize is the dynamics here, and the fact that in the limit, the dynamics can be quite different and heterogeneous across models. So think about these as at least well-defined up to scale, but then but up to scale, there's big differences, going between 1.5, say, and 2.8. So there's a huge range of values here that matter. I mean, that show up in these calculations. Okay, now what I'm going to do is I'm going to take, yeah.
If there is no any kind of reaction, does it mean, for example, that in maybe 20 years, the degrees would go 10 Celsius up or something like this? Is this the basic assumption? Because we see the declining after this steep increase, after let's say maybe 5 years, all model go down, there is downward curve. So if there is no reaction in maybe,
no, these
we have 10 degrees more.
So there's nothing going on in terms of human actions or anything else here. This is literally take a client, a geoscientific model, and put in these exogenous impulses of CO2 into them, and just see how those models respond to it. But there's no notions of an economic response that come out of this. So this would not be the impulse response function that came out of our model that allowed for the economy to respond to these shocks or these.
And apologize for the ignorance, but how do we determine that we are at the point zero?
I'm sorry, how do you describe what?
How do we determine that we are at the point zero?
That we're at point zero. So they all take some initial date. I forget what it is, whether it's 2020, 2010 or something, or 2015. I forget the exact date. So we're looking at this from the climate literature. They all start their model simulations at a given date. They're given a size of a pulse. They feed it to their models. That they report what the responses to the models are of that pulse. And these are completely geoscientific models. There's no economics in them. So all I'm trying to do here is to characterize the geoscientific uncertainty here.
Yeah.
Now, on the economic model I laid out, there's going to be economic responses to things and the like, right? So it's not.
But let's say I assume the year is 2015 when these models, when you do the same thing. Can I say that now we are the declining part of this temperature? If we move 5 years in front, then it seems like it's declining. So it depends what this point zero is. Is it?
Yeah, I think the actual point here between, if we buried it over a full decade or two is not going to matter very much. Which I think the size, what could matter more is the size of the pulse. Okay. Now these are all pulses relative to some type of baseline, and so we could debate over whether they got sensible baselines, which they're starting from or not.
Professor Hansen,
but for fully linear models, then none of these issues would matter. So your issues have to do with how nonlinear these models are, and in terms of how sensitive they are to various initial conditions and the like.
Professor, may I ask a question?
Yes.
So I understand this is an impulse, but I guess in reality, if the climate increases by 2 Celsius degrees, and then the global warming situation will be more and more severe, more quickly. That's the reaction. Going forward after 20 years, 40 years, if we don't change our policy, so it will be more and more severe and more quickly.
Okay, so emissions are going to happen every time period. This has to do with increasing emissions in a single time period relative to some baseline. It's a way to summarize dynamics, just like we do impulse responses. Right. But and it's going to show you that the impact of that change is, maxes out over 10 years, which is been somewhat of a revision coming out of the climate science literature if you compare it to what we look at now versus 10 or 15 years ago. So these things are resolving. So these things hit their peak impact fairly quickly. Now, there's a model here that would be a very simplified characterization of this, is just imagine that every emissions has a permanent consequence on temperature, and there's a coefficient that determines that. And this is telling you what that coefficient is. Now, that's not literally what happens, because it's this ramp up piece. You don't jump up quickly to this level curve going on here. But you're not too far away from that, because this is unfolding over such a fast time scale that from the standpoint of social policy, and with low discount rates, the initial uptick is not going to matter that much. But all I'm trying to do here is characterize uncertainty about climate dynamics. There's different ways to represent it. This is one way to do it. So now what I'm going to do is I'm going to take the discounted value of this, using the same subjective discount rate that we use in our preferences, and I'm going to I'm going to discount these paths, because in simple models, that's what's going to be germane for the social cost of carbon, and then I'm going to convert that into an exponential average. It's just going to be a different way to represent the uncertainties, because that's really what matters to the planner in some sense. And so I'm not going to, so every one of these curves is going to be mapped into a number, and I'm going to give you a histogram over the numbers. And that's this. So these climate sensitivities are ranging from 1.7, 1.8 in the median. It can go down, they go down, they can be as low as 1, they can be as high as, something, 2.7 or 2.8. So there's a big range in these things, consistent with what you saw in that previous diagram. So these are just histograms of the 153 different models which we get. So abstracting from uncertainty, we just shoot it. We would just take the median point here and then pretend that's the number. Now these histograms, we've weighted all models equally. Maybe some experts would say some models ought to be weighted more than others. It would probably be difficult to get all experts to agree which models ought to be weighted more heavily, but for the purpose of our calculations, our so-called baseline that came up before is we're going to treat all models symmetrically, and then we're going to move away from that. Okay, so this is going to be input in those calculations. That's the input in terms of how we go from emissions to temperature, and then I talked about how to go from temperature to damages, and there's uncertainty in both pieces of these. And these two pieces multiply together, right? These are kind of multiplicative in nature. So now what we want to do is quantify the impact of uncertainty. So I'm going to compute, to do that, remember the social cost of carbon can be viewed as an asset price. This discounted social consequences of marginal consequences of emissions. So coming off my kind of prudent or robust decision problem was that change of measure, that uncertainty adjustment. That's going to be the social cost of carbon that emerges from the computations that corresponds to what the social price should be according to this this model decision making. I'm going to then compare that to, suppose I took the same emissions trajectory, same path of these economic responses to emissions going forward, and I'm just going to discount them I'm just going to average over all the models with the original, treating all models equally, and then draw that comparison.
Lars, I have a question to you about, first of all, maybe you want to look at median rather than average.
Median's fine too.
And then what about the standard deviation of all of those models when they give their numbers? How certain are they about their point estimate?
That's a good, a lot of these models are deterministic models. They're kind of near chaotic models. It's not so easy to do straight statistical inferences off them because of the way they're built. Now there has been movements more recently to try to put random impulses into their models, as well as this kind of nonlinear dynamics.
Another question I have about this 153 are some people are repeating their their way of estimating, and as a result, maybe it's biased towards some authors that are doing the same stuff and are either at the upper level.
So how these models are calibrated is a fairly complicated thing. So I don't really, to open the hood on that would, so what you're saying is there might be some, some models might be a priori more overlapped and connected than other ones, and maybe that should lead you to a different type of weighting. Maybe two models are essentially the same model, and maybe therefore you shouldn't be treating them as distinct models and the like. So that questions whether we ought to be doing this equally weighting of all models. Now we're going to start with the equal weighting and perturb away from it. Now one could, with a lot of effort and judgment from climate scientists, it would be tough to get any type of consensus, maybe figure out different weights to assign to all these different trajectories. I think that's that'll be a hard thing to do in practice, but yes, so more thinking about the subjective inputs here could be advantageous for sure. Okay, so anyway, what I've described in the slide is a way that we can quantify the impact of uncertainty on the social cost of carbon. I just compare those two different expected discounted values and see how big their difference is. And I'm going to be showing you some pictures like with that as well. Okay, so let me just start off with the following. We're going to take our model and we're going to do two things. We're going to first imagine we're going to take ambiguity neutral. So instead of doing all that, that robust adjustment to how we weight models, we're just going to use the original weighting. 50-50 across the two damage specifications, all 153 models weighted equally. Solve for the course of action. That's the so-called ambiguity neutral case. And that's the red line. Now, and so this is, this is the projections, the recommended projection course of emissions coming off this kind of planners, social planners, or hypothetical policy problem. Now I'm going to induce a form of ambiguity aversion, and not surprisingly, that's a theory of caution. That's going to lead a movement from red to blue, which is lower as we expect. Now, how the social cost of carbon? I'm going to do the same two things. Okay. The blue is going to be the ambiguity averse one, and the red will be the one that's we're just going to simply use the simple averaging across models. Now, the social cost of carbon here increases, and increases because even though this is coming off of solving a prudent problem, we eventually start damaging the environment, and then as we get closer and closer to the places where the damages become more severe, the costs then start increasing on you more and more. And so we kind of expect this upward trajectory here. And then what shows up here is that under the neutral case, then that trajectory is going to be lower than under the averse case. Now, this comparison as a price is a little bit tricky. Why? Because there's different, we're evaluating these kind of marginals, so that we're evaluating these two different social costs at different emissions trajectories. Remember, the ambiguity neutral emissions trajectory was higher than the ambiguity averse ones. Okay? So this alone doesn't tell us how important uncertainty is, because we've changed, or at least it does so in a fairly indirect way, because we've changed the corresponding emissions paths in which we're computing these to these discount expected values. So next, what I want to do is hold it fixed. I want to do this uncertainty decomposition. I will go to my averse case, and I'm going to take the total. I'm just going to plot that again. And then I'm going to do this calculation I talked about before. Just change now the probability specifications. Okay. The blue solid one has this conservative adjustment in probabilities. Okay. The one down lower then says, well, suppose that instead what I've done is just use took the same social cash flow, but then just use the original set of probabilities, the simple averaging across models, and then I look at that difference. That's the uncertainty component here. So at least for these calculations, the uncertainty component's a very sizable chunk of the total social social cost of carbon here. Now you might be worried, maybe we rig things to be extreme. Maybe we just made our policymaker way too averse to uncertainty, and that's what's driving this. So we want to say more about that, and that's what I want to turn to next. But let me make sure we're all on the same page here before I go further. Listen, any questions about these figures?
Right. Any question? Radosolv, did you have a question? Dimitrik? Radosolv? No, okay, I don't know. You can go on, Lars.
Okay. So now what I'm going to do is I'm going to show you what happens to the probabilities across the, I'm going to, remember that histogram across 153 models. So what goes on here is part of the calculations is we're going to start like tilting that, we're going to start like moving that histogram around a little bit, shifting probabilities in it, shifting probabilities in ways that are induce a form of caution. That just comes out of the calculations. So I'm going to start off with what that shift is at 50 years, where we're at 50 years, they're given we're on a prudent path. We're not yet having severe damages of the environment. And what we've done here is the blue lines are telling you, this has moved a little bit fast here. Let me just go back. Sorry. The red lines are telling me what the original probabilities were. The blue ones on the right are showing that I've shifted it from the left to the right. I've made this cautious adjustment. Okay, but it seems, but before this takes off, this seems like a fairly modest amount of movement here. So now what I want to do is unleash the thing. I'm going to see what happens after I go from year 50 to further and further timescales. I'm sorry, I got the timing off here a little bit. But so anyway, I start off with these very, very tiny changes in these histograms, just weighting things a little bit, with the blue ones, weighting things a little bit more heavily towards larger climate sensitivities. And then as I get more and more ranges, as I further years out, I'm in more and more damaged regions, and now I start damage the economy more and more. So not surprisingly, you're shifting probabilities more to the right. And now by year 100, that probability shift is much more substantial. So part of the assessment of, is this a reasonable amount of ambiguity aversion to induce, has to do with looking at figures like this. How crazy do you think these type of shifts in these histograms are? If you think these are just totally nutty to after year 100, put all this weight on, to put a little bit more weight here on these higher values of climate sensitivity, then what you want to do is reduce the amount of ambiguity aversion. But so it's this back and forth you can do between how much ambiguity aversion you have and how much you're at the end of the day shifting these probability distributions as they then play out over time. And so that's part of the diagnosis and calculations you can do from the setup.
Lars, again, what is this red stuff at above the purple?
Okay. Now my movie went too fast, so let me now that it's stopped, I can let me talk this through. Okay. The red ones here are, so the red ones are on the left, give us the original histogram heights, okay? Now, once the histogram changes from red to blue, the red ones are just now purple because that's the overlap between red and blue. And so now just take the purple ones on the right. So take red on the left and purple on the right, that's the original histogram. Mm-hmm. Now take purple on the left and blue on the right, and that's the tilted histogram after 100 years. So this is just showing the tilting. And so if I go back, I start here with very modest tilting, and then as this plays out over time, it just shifts more and more. So these are the type of outputs which you can do. Now at the same time, you're also reweighting that high and low damage model. If you recall, I said that you start off at 50-50. I think at the end of this, you're about 60% on the high damages and 40% on the low damages. So you're also moving that probability a little bit as well. So these are the type of calculations that help us figure out what's our sensible amounts of aversion to this uncertainty. Okay.
Yanis, you have a question?
Yes, apologies if you have covered it already, but what's the alternative scenario based on which you calculate the negative impact of carbon? Like you compare the negative, like you use the carbon in this time horizon,
Yeah.
and you say that it induces some negative costs on the economy.
Yeah.
What do you compare that to? What's the alternative?
Oh, okay. So what we're doing here is we're solving the model out. So in fact, let me just go back further to the early emissions ones. We're solving the model out, and the emissions trajectory, we're taking the emissions trajectory off of the model. Now, if it, in this particular model, you would, absent the climate problem, absent climate change, would have a nice balanced growth trajectory, and so emissions would behave in a very stable fashion, and that would lead to much more, damages occurring much faster than what happens here at a higher level of emissions. But so what we're doing is we're looking at the along the socially prudent trajectory of emissions. Now you might ask, suppose, well, what I really want to do is I want to look at what I think is, I don't think we're on some socially prudent emissions trajectory. I'm going to be on some other emissions trajectory. I'm going to go with that one and then ask how important policy could be relative to that trajectory. These type of methods that we talked about here can do, we could do that either locally or globally. These pricing methods would basically correspond to a local counterpart. What happens if we made a small policy change, then what would be the outcome? So a social cost of carbon measure there would be much more like a local, what would happen for a local policy change away from us from a suboptimal trajectory. If you look at the literature on social cost of carbon, it's a fairly incoherent literature. It's different. It's different. It means different things in different settings. Sometimes people want to use market prices to do these discounted present values. That's different than the Pigouvian tax type calculation. So here we're going along the socially efficient trajectory and then looking at the wedge between the private and social. So the path we're talking about is endogenously determined.
Okay, so but the reason I'm asking is because as an economist, you don't only care about the environment, but you have a set of needs and desires for the polity or society that you're dealing with that you need to satisfy them, right?
Yes.
So I think, and correct me if I'm wrong, that you only look at the cost, the environmental costs, but I think you have to put the entire economic equation down. Like you have to feed people, you have to house them, you have to keep them warm, and if you don't have an alternative to the carbon use in order to satisfy this primordial economic needs and desires, then you cannot really talk about social negatives of the. I mean, because if you don't use carbon, then you may actually people be dying, and that's another even more negative part compared to the carbon choice. I wonder what gamut of economic needs does your model satisfy? That's what I'm trying to understand.
Give me a couple slides because I want to turn to that. I think that's a very important question and consideration. It has to do with the limits of this model versus what can this model tell us versus what richer models can tell us. Okay, so this model it's not the case. Anything having to do with this, these trade-offs you're talking about get loaded into this so-called damage function of kind of Nordhaus and Weitzman, and that's a very ad hoc way to go, and I think it's and one would have to in part open the hood on those type of specifications, and I think it's important to push beyond those. But let me come back to that in just a minute. I think it's a very important question. Okay, so let me just take inventory of what we have. The social cost of carbon can be magnified by prudent social planner or stand-in for a policymaker who does not have full confidence in assigning probabilities. Resulting uncertainty component of the social cost of carbon can be sizable depending upon the presumed aversion. The planner implements the ambiguity aversion by replacing baseline probabilities with their adjusted counterparts. And the adjusted probabilities provide a revealing assessment of the magnitude of the aversion. So that's kind of what I want you to take out of the current calculations. Now the model we had was a model with a single technology. It's a model in which emissions both are good but they also damage the economy. So there's this kind of trade-off between the good and the bad here through emissions that's kind of worked out by the policymaker. And that's kind of the nature of the whole calculation here, having to do with, trying to work through that trade-off, taking into account the fact there's uncertainties in terms of the environmental damages, as well as uncertainties in the geoscientific inputs. But this model's highly missing some stuff, and this stuff can be important. So for instance, one could imagine a situation in which you've got two technologies, maybe a clean and a dirty technology. And at some point in time, you might want to transition from the dirty to the clean, shift away from fossil fuels and towards renewable energy. Now, this might happen just as we kind of start raising. This might happen kind of naturally because these renewable energy becomes more productive, or it may come through different sorts of policy actions. I think putting this type of transition here, not only it pushes us beyond this kind of what is the implicit Pigouvian tax rate to does it make sense to be subsidizing renewable energy or not, and if so, by kind of what magnitude. Also, part of that decline, when you had emissions into the atmosphere, there's an initial decline because of sink capacity and absorbing of CO2. Maybe the type of investments we should be thinking about have to do with ways to increase that sink capacity, or say enhancing resilience through biodiversity and the like. Maybe those are the type of policies that might be most prudent. Those are off the table here, but I think it'd be very interesting to put them back on, or to put them on. Finally, I think this has to do with the previous question, resilience and adaptation. What are the endogenous economic responses to climate change, both positive and negative? And the static damage functions are kind of useful for some preliminary calculations, but I think it's important for the economics to move beyond them to thinking more seriously about modeling resilience and adaptation as we change the environment. So these are important things to be doing. It's easy for us. These become computational challenges, ones which we're trying to confront and address, because we think this can lead to a much more interesting. This can enrich some of the policy discussions beyond just the what's the social cost of carbon. These extensions will, however, open additional channels with uncertain consequences. They're not going to resolve the uncertainty. They may change the nature of the policy challenges in important ways, but they're not going to immediately make uncertainty irrelevant. They're also, the social cost of carbon is still going to be a relevant construct there, because it's still going to be useful to see how alternative policies, how far they go in closing the gap between the actual prices and the idealized notions of the social cost of carbon. So I still think these these social cost of carbon numbers can still be useful. It's just that once they put different policies in place, that wedge is going to be shrunk. And how much it's shrunk, I think, is an interesting thing to note. So uncertainty is not going to vanish in these discussions. I think the policy question can be made richer, but uncertainty is still going to be present, and potentially in very central ways. Okay. With that, I think I'm going to end.
Lars, in every time you say social cost of carbon, you mean social cost of carbon minus the social private cost?
No, this is the total social cost. In the model that I'm writing down, the private cost is tiny. But
it may be important because people.
What I'm talking about here is the social cost, whereas you want to think about taxation. The taxation has to do with more the wedge between the two. And as we put other policies in place, then of course that gap between the social and the private is going to start diminishing.
Right. I'm just thinking that the private cost is maybe people are dying in Beijing relative to Shanghai because of pollution.
Is that a private or a social cost? It sounds like a social cost to me, but
I look at it as private. People are dying. But you're right, there is some social cost.
I mean, why is by private, I mean, is the market internalizing it?
Yes, I assume. people are moving from Beijing to Shanghai and the mountains.
Well, that has to do with the adaptation question, and absolutely.
Right.
I mean,
Okay.
this is
Yeah.
this is something that's not in our model explicitly, and I think it's important to push this whole literature in directions like that.
Okay.
So let me just end with a quote from a famous U.S. author. Education is the path from cocky ignorance to miserable uncertainty. Uncertainty can be miserable, but there's ways to confront it and cope with it that can be productive. So with that, I'm happy to take more questions. Or
Okay, good. So there are some students who were assigned to ask questions, so go ahead.
Yes.
I don't see all of them. You, go ahead.
Yes, there's a question from the student. Would you like to comment on how model misspecification could impact on uncertainty, and which framework can be used to integrate model uncertainty and model misspecification into decision making?
So what I talked about today was focused much more on the model and on the model ambiguity side instead of the model specification side. There are a set of tools that that have come out of robust control theory that try to address the model specification part, which Sargent and I've used in some of our previous work. And that can be integrated into this. We haven't done that in this particular paper. We have other papers. Brock and I have another paper that focuses just on the opposite effect, the model misspecification effect, which is also, it can give different implications, but it's also a theory of caution because you're not sure that the model is quite correct. And in a principle, the two could be integrated along the lines described in the paper, in the background paper. And so there's potential methods for doing that, but in the calculations here, I've not done it. Now the way the model misspecification approach works is you imagine that you use some type of criterion like a likelihood ratio. You entertain statistical departures from the baseline probability specifications that are small in this kind of relative likelihood sense, but very flexibly specified, and see what and then see what their consequences are.
Where is you?
Yes, another question is the impact of climate change is likely to vary across countries.
Yes.
I mean, how can this model be extended to account for such regional heterogeneity?
Yeah, that's a very important question. So this is like a worldview model, which is clearly has huge limits. It's very clear that climate change affects some regions, some economies very differently than other ones, and the like. And my co-author Buzz Brock has done some important work along this direction already, but not with the dynamic richness that we have here. So down the road, we really want to kind of merge some of his kind of geographical approaches to things with these dynamic approaches, which we've talked about here. Again, our biggest impediment right now is to be able to do this in a way that's computationally tractable. But yes, absolutely, we need to be putting some type of differences in exposure to climate change, going across regions or economies or the like, and because we don't expect climate change to be affecting everyone the same way. So it's a terrific question. It's a direction we want to go. Again, abstractly, I know how to do it. The biggest impediment we have right now is figuring out how to make it numerically tractable. But we're working on it. We're thinking about it at least.
What about changes in the discount rate? Because maybe the young generation cares more about green economy relative to us, the old guys.
Yeah. So there's a discount. So in these, so this whole literature on environmental economics, what is the discount rate? Gets a few different things confused. In an uncertain environment, if I'm looking at even social cash flows that are uncertain, there's not a single discount rate. Because how you discount depends on your exposure to the uncertainty. But on the other hand, when you write down the preferences, there is a subjective rate of discount inside those, and that it's straightforward for us to move that and push it even lower than it is now. And yes, that can have that can crank up the cost for sure.
and the investment in J and in increasing J, you know, out like exogenous change in J because people are more aware of it.
Yeah.
You go ahead. Next questions.
Yes. So in practice, how can we get a good calibration or estimate of the parameters in the models in the paper?
Yeah, good question. So we're treating these climate models as something what of a black box. They're fairly big and complex, but they generate predictions. And we're just taking it to hypothetical pulse experiments and other type of experiments. And we're just taking the output of those. So there's one could within those models, one could imagine, you know, trying to do estimation inside each model, and then from there figure out posterior things like posteriors overall, you know, the climate sensitivity parameters we care about, these impulse responses, and then go from there. We don't have access to that, and in fact, those models are often not even well set up to do that because they're, as I say, they're nonlinear deterministic models. But in principle, that would be interesting thing to be doing for sure. On the economic side, then, you know, it's the same issues that we face, or that, you know, ones that macroeconomists face, but there's these damage functions. And I think we know the damage function with any certainty. That's quite clear. That's just not true. And so what's the right way to estimate damage functions is something that there's lots of discussions in the environmental economics literature, but it's hardly a settled issue. And you know, more and more they're pushing towards damages that are kind of region specific. So for us to catch up to those measurements, we have to have a richer model with a more geographic or dispersion.
Can I ask a question about solution methods? So you did not mention which solution methods do you use for solving these 153 models. So I'm asking because I know some people in this literature, they argued that you cannot really use perturbation or linear methods. They were criticizing Nordhaus for his analysis. Yeah.
Okay, so there's two things here. One is 153 models we're taking as our input is basically that discounted impulse responses from those. Yeah. So we're just taking those models. We're not solving their models. We're taking their model outputs, and from those model outputs, distilling the outcome of those pulse experiments and feeding those in to our calculations. Now, from the economic side, there we have to solve things, and that's there things can be quite costly. It was the paper in the background. We put a lot of effort on the computational side in the paper, in the background paper. Do I think we're necessarily doing it the best way? I certainly hope not, because I want to expand the dimensionality of the state space in an important way. But in a very crude nutshell, there's a type of iteration scheme going where for a given set of probabilities and a given set of decision rule, solving the PD is like solving this very high dimensional linear system. So we kind of iterate back and forth between solving that linear system versus then going through and figuring out new guesses for the changes in probabilities and new guesses for the decision rules for how much to invest, how much to explore, how much to omit, and we kind of go back and forth between those two conversions. Now, that doesn't always converge. We have to adjust step sizes, do false transient refinements and stuff like that. So so sketched out, there's kind of a Jupyter notebook attached to our paper in RFS that gives the full characterization of what we're doing there. We think there's probably better ways to do things for solving these PD problems and of other types. There's been a lot of push recently to try to build in neural net type methods to try to deal with much larger state spaces. We're anxious to explore those methods we're trying to engage computational experts to help us do this, because we do need to think hard about expanding the states, expanding our dimensions of our state to be able to address those extensions I had on one of my slides.
Professor Hansen, I have a question that is in the form of a terminological remark.
Okay.
When I was in primary school, we learned that climate refers to periods of, 500 years, 1,000 years, but
Yeah.
just about every climate talk, the span is a human lifespan of about 100 years, which to me is really weather. Now, the models are excellent. It's lots of math, good economics, and all that. But, when it comes to applying this to real life, these models may amount to weather chasing. It's like you're playing stock market by timing it, right?
Yeah.
And so perhaps we need to get into this habit of replacing this terminology climate by saying, okay, what we mean by this is human lifespan of 100 years.
Yep.
And
yeah.
The climate has been modeled by Milankovitch's theory. It's due to changes in climate are due to astronomical elements such as precession of the Earth's axis and other elements. And that theory has been not surpassed so far. And so when it comes to climate, that's it. But so weather is probably more appropriate for all these talks and models.
So I have a few reactions to that. One is, it's absolutely right that what's long-term for an economist is short-term for a geoscientist. And they often crank their model out, simulations out for many, many centuries, which an economist would never trust their model to cranked out for many, many centuries. And so the timescales for which are hoping to explain phenomena can sometimes be quite different. And then becomes a question, how far do you want to push those models as a way to think about what's going to happen over multiple decades or up to 100 years or 150 years or whatever that we think is the right timescale. So that is a good question. We are following some of the, we are using the output of those models, maybe cranked out to 100 years, 150 years, which our model simulations also include. But maybe those models, since they have a longer time scale in mind too, are focusing on the wrong ingredients. That's possible. We've been talking to some geoscientists that are emphasizing much more nonlinearity. Now, does that nonlinearity play out over decades and centuries, or does it play out over, when you think about ice ages and the like? There's non-trivial issues there for sure. So, when you say it's weather, I guess I agree. Temperatures, in some sense, weather. The question is, do emissions affect weather? It's true that the effect could be disguised by other sources of weather fluctuations. And so that certainly not all temperature changes are due to climate change. We know that for sure. And we know there's even low frequency movements in weather as well. So distinguishing what part comes from climate change versus what part comes from other fluctuations in the weather is already a challenge for sure. I would agree with that. That's part of the challenge of doing research like this. I still find it interesting and valuable, but I'm aware that the timescale issue that you talk about.
Okay, Yanis, sorry, 1 second. Yanis, do you have a question?
Yes, I have actually 2 questions. The first one has to do, it echoes a question by Johanna on private costs.
Yeah.
It seems to me it would be more tractable if you only assigned private costs. So what's the cost of the private individual of climate change, emissions, environmental impacts in terms of health, economic prowess and all that stuff. And then if you need to also assess the social cost, then do an aggregate of the private costs. Would that be more tractable, or is that something that you think is worth?
I should have been clear how I'm using this term private cost. Imagine that you've got a market economy. A market economy, we know there's a so-called invisible hand, and then there's connections between market prices and in certain environments, social efficiency. Now, when I think about private costs, all I mean is the costs that would emerge in a market-based economy without any intervention, or with suboptimal intervention, and compare that to what happens to the socially optimal cost. And that's what I'm doing here. Now, what type of cost you want to look at is a different question. I mean, that's I absolutely think that health is part of the impact of climate change. If you think about China, for instance, China is very concerned about air pollution. That people say, well, China is more concerned about climate change. Well, in part because of the implications for even short-term health considerations through pollution and the like. So, yes, we want to think about different forms of different forms in which climate change can impose costs on people in different ways. And so that's part of doing a better job of thinking about damages associated with climate change and getting richer ways to characterize those. So again, by private cost, all I meant was what would be the cost coming out of market outcomes.
Professor,
okay, one second. May Lee, one question, and then Yanis, your second question, and we have about 3 minutes to go just to make sure. Go ahead, May Lee.
Okay, thank you. So Joe Biden has pledged to spend $2 trillion to slash emissions during the election. And in China, President Xi also pledged that China will achieve carbon neutrality before 2060. So when we model different countries' policies, should we consider their political system? And do you think China has higher probabilities of achievement of its climate policies? And do you have any probabilities in mind that the US and China can achieve their goals?
I'm just going to answer this in 30 seconds. So, okay, you're asking a very important question that's not part of this research. That doesn't mean that I don't think it's fundamentally important. You're asking a very real policy challenge that we have. We have different governments, different priorities, different governing systems, and how can we imagine they're going to coordinate on some type of sensible climate policy that when climate impacts might carry over, might even have global implications. I would agree that the policy levers available to China and the policy levers available to the US or Western Europe may well be different. And that's something that one should take into account. How to best coordinate policy across different governments, that's a political economy question. It's a very challenging one. We could imagine building versions of the different economies playing dynamic games against each other and trying to, in terms of the design of policy. And do we want them to play symmetric games, Stackelberg games, or what's the right way to go? We could impose different policy constraints on the different type of entities as well. So I think all those models are fascinating. I got to do stuff that's tractable. So I think the political economy question is a very important one. This paper just wants to show that uncertainty can be a big issue. And one that we should not leave in the back burner. But I would agree with you that this highly stylized kind of worldview of the climate change policy has enormous limits to it.
Okay, Yanis, one question and 1 minute answer because we are almost at the end.
Yes. Yeah, to echo a little bit Radovla's skepticism on the interpretation of climate impact. I see a fruitful field for economists to study the problem of emissions by seeing emissions as occupying space, like your emissions occupy space on the commons, which is the atmosphere. And then could you have assigned costs that way and then assign proper remuneration or taxation for occupying space that's not yours and it's commonly owned?
So basically what you want to do is you want to go up to space and allocate property rights or something, and that you have the right to do what the heck you want to your part of space. Is that what you have in mind?
No, the space is atmosphere belongs to everyone equally.
Yeah.
And belongs and should belong also to the future generations. But when I put emissions, then I occupy that space at perpetuity. So I should be charged for that.
Right.
Because I occupy space that's not mine by dealing the atmosphere as a commons.
Right, I agree.
Do you think that would be a tractable way to assess costs?
Well, I mean, to some extent, that's what's going on in these calculations. In the sense you think that emissions cause this damage to the climate system, and that somehow ought to be taxed or there ought to be costs borne on it. Now the problem here is we don't have enough heterogeneity, so it's not brought. This is like there's one cost which are say should be applicable to everybody. The other way to, I guess the other way to go is a so-called cap and trade. We allocate emissions rights across different countries, and then they can trade them within and outside countries. But I do think the way you're thinking about it is probably not too foreign from what people hope to have in mind with this, this kind of highly stylized Pigouvian tax problem.
Okay, good. Christos, do you want to say a few things before we complete?
Well, Lars, we're very grateful for your talk. We really enjoyed it. Thank you all for participating. We're really honored to have you with us, and we certainly hope that you're going to visit us again.
I hope next time I actually can visit you in reality instead of virtually.
Yes. So just a full disclosure.
It's the same here.
Very good. So just a full disclosure, I know Lars from the time of studying in the University of Minnesota many years ago. I still remember Chris pushing Lars not to talk to us, because at the time we already knew that he's going to do very well in the job market and so on and so on. So I'm really happy that I have Lars today, really closing some kind of a circle. So Lars, I want to thank you again and appreciate your time and everything else. I would like to thank all the participants, especially the students who submitted questions, and everyone else. And again, we are looking forward for next week, where Milos, who is participating here and was a former of City University of New York, alumni of the Graduate Center, is going to present. A week later, as I mentioned, James Heckman and Richmond will present. And then at the end, we have Finn Kidland from California, presenting another Nobel laureate, which we are really under this historical semester, I think. Thank you, everyone, and have a nice afternoon.
Thank you, Lars.
I want to thank also Christine, who is the executive program, I think, right? That's her title, but she's really running the show behind the scene. And of course, I'm sure Lars is thanking, what's her name, Lars? You need to remind me.
Valentina and Diana are the people to
Valentina and Diana, yes, very good. So thank you, everyone, and see you next week. Bye.
Thank you.